Hello everyone, my name is Frans van Die. I'm a PhD student in the group of Professor Vincent de Jacques in Haifa and the Technion. And today I would like to talk to you about our recent work focusing on the detection prospects for the gravitational wave background of a galactic population of subsolar mass primordial black holes. Now, first, a brief introduction. Why PBHs? Primordial black holes are compact objects that are hypothesized to have formed in the very early universe. And now in our work, we focus not on the formation mechanisms, we remain ignorant to them, and we just assume there is a population of PBHs directly after inflation. PBHs as a concept were introduced in the 70s by people as Hawking and Carr, and ever since the detection of black hole merger events or gravitational wave merger events, they have gained renewed attention. And especially subsolar mass black holes are of interest here as they are a strong indicator of a primordial origin, since subsolar mass black holes are very hard to form astrophysically. Now, PBHs can make up a fraction of the dark matter spectrum, as summarized in this graph, where on the y-axis we see the fraction that PBHs can construe the dark matter spectrum, and on the x-axis the mass of the PBH, and in this figure it is assumed that all PBHs are made up of the same mass. And this is an assumption that we will also take in our work. Now here we focus mostly on mass window C, and to make it more explicit, we take models where the PBHs have masses ranging from 0.01 to 1,000 solar mass. And the mass fractions are taken to run from 10 to the minus 4 to 10 to the minus 2, so 0.01 to 1%. Another side note here is that we focus only on early type PBH binary systems, which means that these are binary systems that form in the early universe, or in the relatively early universe, as you will see. Contrary to this, there's also a late time PBH binary population, which forms in mechanisms that are much more reminiscent of astrophysical binary formation mechanisms. Now, if we define eta naught as a binarity parameter that signifies the fraction of PBHs in the Milky Way dark matter halo that live in early type binary systems, we can estimate the number of these binary systems we may expect there to be in the Milky Way dark matter halo as follows. And we will come back to this once we have a better estimate of the binarity parameter. So the steps that we have to take are, first we need to initialize our PBH binary population. Then we have to evolve this to the present day epoch, to the Milky Way dark matter halo. And lastly, we need to predict the gravitational wave background signal, where we focus mostly on the LISA experiment. So let's start with the PBH initialization. We assume the PBHs to be distributed in a Poissonian manner, so no initial clustering. And a PBH and its nearest neighbor together are called a PBH pair, and these may form a binary. We also give the PBHs some initial angular momentum directly after inflation in two ways. One is via the interaction with other PBHs, which is modeled as a power law. And second is by the interactions with the smooth dark matter component, which is modeled as a Gaussian process. Now, if you say that R is the distance between the PBHs within a PBH pair, we model binary formation in a Newtonian approximation, meaning we have the following equation of motion, where here we have the Hubble friction and we have the gravitational interaction. And also we have a angular momentum barrier that counteracts the gravitational interaction. And we note here that the angular momentum barrier is actually time dependent in the matter domination era, since the smooth dark matter component has a time dependent RMS variance in that era. Now we say a binary forms once it decouples from Hubble flow. And at that point, we have a binary with some semi-major axis, some formation time, and some eccentricity. And then we can evolve this binary to the present day epoch. We do this purely with a gravitational wave evolution, and we do this to get rid of the binaries that would have merged by the present day epoch. So the hardest binaries would have gone because of this evolution effect, and we are left with only the softer binaries. And this is what is visualized in this graph, where first of all, we note that binary formation stops at around a redshift of 100, as here is the scale factor normalized to unity at matter radiation equality. So we don't have to worry about any nonlinear effects. Secondly, we have here lambda, a dimensionless parameter, which basically parameterizes the initial separation of the PBH pair. So we have our two random parameters. We have the separation on the x-axis. We have the initial angular momentum on the y-axis. And here in black, we have the PDF. And in this parameter space, we see that everything to the right of this colored part will never decouple into a binary. They are too wide, or they have gained too much angular momentum to ever decouple into a binary. And everything to the left of this diagonal part signifies binaries that are either too circular or too closely separated, hence they would have merged by the present day epoch. However, this is only about 10% of the total PBH population that would have merged by today. Now here in the top figure, we see the semi-major axis in AU in the color scheme, and in the bottom axis, in the bottom plot, we see the present day angular momentum parameter. And one thing to note, first of all, is that we will see that the binary population that remains unto the present day epoch is very wide. It can reach semi-major axes of about 10 to the 4, 10 to 5 AU, and also very eccentric. So we have a very wide eccentric population of PBH binaries. Now, another evolution effect that we have to take into account is possible interactions with the stellar population in the Milky Way. Now, we model this by including a stellar disruption, a deterministic stellar disruption with the present day stellar population in the Milky Way. And this can happen in two mechanisms, either via ionization or via evaporation with its interactions with stars in the Milky Way. And we say that soft binaries are disrupted once the combined rate of these two processes exceeds the Hubble rate. A very important thing to note here is that this disruption process is, of course, a location-dependent process in the Milky Way. Since both of the disruption processes that are accounted for are dependent on the stellar density in the Milky Way, and hence, depending on where the PBH binary ends up in the Milky Way halo, the disruption will kill more or less of the remaining population. Also, I must note that this is an orbit averaged approach that we take here. So the result of this process can be visualized in this graph, where I took just 3 random positions in the Milky Way and looked at the effect on the binary population. So here we have on the x-axis we have the present day semi-major axis. On the y-axis we have the present day angular momentum. And here on top I took a location in the Milky Way bulge. In the middle I took a location in the solar neighborhood. And here on the bottom I took a location in the Milky Way halo. Now in the halo, the stellar density is too low to have any impact on the PBH binary population, and we see that nothing nothing of the population is killed due to disruption. In the solar neighborhood, the stellar density is higher, and everything to the right of this line. So the widest binaries are removed, and also in the bulge, basically everything is removed. This is a log color scheme, and hence we can see that basically everything of the population is gone. One other thing to note here is that because of the gravitational wave merger or the gravitational wave evolution effect, we see that some part of the population has hardened, and this hardened part of the population lives in this still towards the more circular and more closely separated binaries. And it is in this still that we will expect to have the most loud signals in gravitational wave data. And lastly, when integrated over all of the Milky Way halo, we see that about 2%, it's fairly model independent, about 2% of the population is killed via disruption. And in this slide, I made the location dependence of this disruption process even more explicit. Where here on the left, you see the visualization of the stellar Milky Way distribution. And on the right, we see a visualization of the of the spatial distribution of the PBH binaries. And we see exactly where the stellar density is highest. We see that the disruption process kills a big chunk of the PBH binary population. So now that we have gone through all of the formation and evolution mechanisms, we can come back to our expression that we had before. And we say that the binarity parameter is a combination of the number of the fraction of PBHs that would form a binary in the first place, times the fraction of PBH binaries that survive gravitational wave evolution, that have not merged by the present day epoch, times the fraction that are undisrupted. And then we see here on the left-hand side a figure of the binarity in terms of our model parameters, and we see it's mostly dependent on the mass fraction and not on the mass itself. And for the number of PBH binaries in the Milky Way halo, we see that it can reach quite high values. But remember that we still have a population of very wide binaries. So the number of binary systems is not everything that's at play here. So we now want to construct our gravitational wave background signal. Now, given that they are highly non-circular sources, these systems emit in very high multiples n. These multiples n can reach even up to 10 to the 4. Energy background of the signal is defined in the following manner. Now we define an effective orbit averaged gravitational waveform in frequency space in the following way, where this gamma function is some complicated function of eccentricity and of the harmonic multiple. And hence we get an expression for the energy density in gravitational waves in the Milky Way that goes as follows, where we sum over all the harmonics in which the binary emits. We have a distribution of our PBH binaries, both in space and in orbital parameters psi, that we have formed via our formation and evolution mechanism. Implementing this gives us the following results. Where here on the x-axis we have the frequency, on the y-axis the energy density in gravitational waves, and we have all of our 15 models depicted here. And also we have the LISA sensitivity curve, which already includes the noise level from double white dwarfs that we know that there is anyway in the Milky Way. Now we see that all of our models do not intersect the LISA sensitivity curve. However, some of the models do intersect the DECIGO and the BBO curves that are also hypothesized space interferometers that, who knows, maybe will be built someday. However, we also see that if one increases F by one order of magnitude, one also increases the energy density by an order of magnitude. So if there would be something with the constraints and f would actually be allowed to be 0.1, we do expect the signal of the solar mass and maybe of the slightly subsolar mass regime to exceed Lisa bounds. But even though in all of our models that we consider here, we don't cross the Lisa bound, there's still hope, since we might expect to see some loud sources. And this is what is shown in this graph, where depending on the critical SNR that one takes, above which one defines a source to be loud, we see a number of loud sources as depicted on the y-axis here. And especially the 0.1 and the 1 solar mass models give promising results here, since if one takes a critical SNR of 5, both of these models predict about around 100 loud sources in 5 years of integration time. Now, also the power law fit that one puts in this left graph has its implications, since if one would assume an isotropic distribution of sources around the detector, one would expect this power law index to equal 3. And now, since both because of the general NFW profile and because of the disruption effects, the PBH binary population is not expected to be isotropic around the LISA detector. We see that this power law index deviates from 3, and we expect that this can be used also as an indicator of this specific population, as a key characteristic of this population. And this is also shown in the second graph, where as a function of distance away from the detector, we plot the distribution of loud sources. And if one looks at the solar mass, so the blue one, we see that these are distributed farther away from us, which means we expect a bigger deviation from isotropy, and indeed the gamma index of the solar mass deviates more from 3 than the 0.1 solar mass model. And in the third plot, we see that the loud sources are still quite eccentric, with a mean eccentricity of about 0.7, but definitely not as eccentric as the general population, which means these loud sources are in the merging tail of the distribution, with separations smaller than about 1 AU. So with this, I leave you with the summary, and I thank you a lot for your attention, and I look forward to the discussions that we may have. Thank you.